Se supone que ya estamos transmitiendo. Ok. Okay, so we will start now. You are ready, Dante? Are you ready?
Yes, I am.
Okay, so welcome everyone. It's a pleasure for me to introduce Dante Kalise from University of Nottingham. He will talk about high-dimensional Hamilton-Jacobi PDEs. So Dante.
Thanks, Alberto. Good afternoon, everyone. I'm very happy to give this talk here. I see a lot of familiar faces in the participants, so a big hello to everyone. Thanks very much for coming this afternoon. Yeah, I'm going to talk about high-dimensional Hamilton-Jacobi equations. I just want to give an overview of the research that I've been doing with many of the collaborators that are named here. Really, it's about control, but it's also about a bit of computation and how have we transitioned from numerical approximation in the most classical sense, like grid-based schemes and related things. And we have been moving towards elements of machine learning, if you want, or deep learning and related applications. So let me just begin here. I always make this disclaimer, although I hope it's clear today that the main point of interest here is how to compute optimal controllers. So my departure point is always here a nonlinear dynamical system, understood in a very abstract sense. So it could be a nonlinear ODE or a partial differential equation, so an abstract evolution equation with initial conditions and control and state constraints. So it's really a dynamic optimization or optimal control framework. But of course, we know that the methodology for this also applies to inverse problems or differential games. And as we incorporate uncertainty on the dynamics or on the cause that we want to optimize, we nowadays talk also about reinforcement learning or model-based reinforcement learning. And what we want to do here, or my interest here, is on the computational side of using model and data-driven approaches to synthesize this control variable. Taking into account the dynamics are often nonlinear and they move across several scales. And with three design purposes, three design principles. First, the control that we design has to be robust with respect to perturbations. It has to be real-time computable. So this is a strong constraint that I'm going to impose here. Although it can be very expensive to compute offline when things come offline, when they come in online in real time, they should be real-time computable, and that the control is somehow sparse or optimal in a certain sense. So here I just have some animations to illustrate my point. So what people are concerned nowadays, for example, is the control of swarm robotics. So this is an Intel project where they would have a swarm of 1,000 drones trying to coordinate a formation in space, like the one that you see there. That's a real project on drone formation that they use for artistic shows like Olympic Games and so on. But here, of course, is evident the robustness requirements, the compensation with respect to wind to achieve a certain configuration in space, and that thing has to be computed in real time. And just for reference, if you think about these drones, they normally have a state space description of somewhere between 6 and 12 states. So if we think about 1,000 drones, we are talking about a 12,000 nonlinear dimensional state space. But also a little bit, I'm going to talk a little bit about the multi-scale aspect. So here's the classical example of crowd motion. So we want to control congestion in pedestrians. But in principle, one can think about this as a microscopic system where every pedestrian has some dynamics, and you want to control through the action, for instance, of policemen or these guys there on horses. But of course, it makes sense from a statistical mechanics viewpoint to zoom out of this system and to think about a fluid flow equation, which is a simulation that you see here, some sort of type of Boltzmann type equation that we want to control. So it's really across different scales. We have the microscopic scale, but you can also think about mean field or transport equations. And in general, this is really at the interplay between modeling, simulation, and optimization. The mathematical challenges are always the fact that the optimization might involve some non-smooth or non-convex objectives. The dynamics are non-linear, and sometimes they are also non-local. So when we talk about these agent-based models, we always end up with non-linear, non-local conservation laws, that there are model uncertainties, and what is the main object of this talk is the curse of dimensionality. So the fact that these are either infinite dimensional problems or problems that are cast in a very, very high dimensional state. So how can we effectively design controllers, optimal controllers for these problems? And I would say this is somehow adapted from one talk of Todorov that from a few years ago. This is really the paradigm here is a trade-off between data efficiency and automation level in the design that we propose. So people working would say in more theoretical approaches, they would sit in descent here. So you have a dynamical system, your favorite dynamics, for which you know a lot of things, a lot of properties, theoretical properties, and you know how to design very good controllers for this. Of course, this is data efficient at most, because you don't need any sort of data. Maybe you just need to know what is the initial condition or some information about the parameters of the system, and then you have a lot of information on what is a good controller. On the other hand, this is not very automated. I mean, you would agree with me that in this setting, if you change the equation, then it's a completely different problem that deserves another type of analysis and study. And in the other side of the picture, you have the more voluntaristic computer science-driven approach based, for instance, in deep reinforcement learning, where you have techniques that are highly automated, so they can be applied for fairly general dynamics without much a priori knowledge of the dynamics that you want to control. But on the other hand, we know that one drawback of reinforcement learning or deep learning techniques in general for machine learning is that they are extremely data inefficient. So training a model with deep reinforcement learning and related techniques always requires like millions and millions of samples with computer power and energy consumption, and things that sometimes are not very appealing. And myself, coming more from an optimal control background where we know what are the dynamics that we want to control, my work, or the work that I'm going to show, is mostly based at the interface on these two things. We'd like somehow to use as much of the theory that we know from the dynamics, but little by little incorporate some elements of learning, but always trying to keep an eye on designs that are efficient in the way that data is used. So because we know that generating samples or data in optimal control is difficult because it will require some sampling of a certain trajectory of a certain control variable, and that can be very expensive as well. So we don't want an approach that requires 1 billion samples of different optimal control trajectories to learn what is a feedback control for the system. So this is very, very, very general. But now going back to the more technical part of the talk, if you want. So what is central here in terms of design, of feedback design, that optimal feedback design is this Hamilton-Jacobi equation, and that's the main point of interest here in this talk. So we can start thinking about a classical problem of infinite horizon optimal control, where we have a nonlinear dynamical system that, for the sake of simplicity, I will somehow have a bilinear structure there, or a control affine structure. But it still has some nonlinearity of interest. And the cost that we want to optimize is an infinite horizon cost with some discount that might be not necessary, with a penalization of the state and a penalization of the control energy. So this is, for example, the typical setting when we want to do asymptotic optimal stabilization to an equilibrium of the dynamics with a feedback. So here, this of course, one can always do necessary optimality conditions and treat this in a nonlinear programming way. But what we're interested here is the use of dynamic programming techniques. So in dynamic programming, the logic is that given a control problem, we derive a value function for this problem. We work with the value function, and we derive through dynamic programming a functional relation for that value function, which in this case is the Hamilton-Jacobi-Bellman equation associated to this control problem, which is this nonlinear PDE here. I'm going to go in more detail now. But once we have this PDE for the value function of the problem, we solve, assuming that we solve this value function, then we can recover the feedback, the optimal feedback, as a byproduct of the gradient of this value function. So the logic here is we have the control problem, we have a Hamilton-Jacobi-Bellman for the value function, we solve the Hamilton-Jacobi-Bellman, we obtain an optimal feedback control as a byproduct of the gradient or a generalization of this gradient of the value function. But of course, the difficult part here is not going from the nonlinear dynamics to the value function or computing the feedback. Once you have the value function, the core difficulty here is the computation, the solution of this PDE, of this nonlinear Hamilton-Jacobi-Bellman PDE. So you see from the control problem, we're somehow now boiling down this to the computation, to the solution of a nonlinear partial differential equation associated to this control problem. So the main object of studying, and from here we jump from optimal control to numerical methods for Hamilton-Jacobi equations, and then to reinforcement learning techniques, if you want, through dynamic programming and through the Hamilton-Jacobi equation. So we have this PDE here. From a PDE world, these are bad news because it's what is known as a fully nonlinear PDE. So the nonlinearity here arises because there is an optimization with respect to this control parameter U. This is not like an easy nonlinearity to deal with. The PDE here is written in a non-divergence form. So even for low-dimensional examples, classical techniques like finite elements and so on, they are not very useful because you wouldn't be able to do integration by parts or anything like that here. And the natural framework, you have here non-existence of classical solutions, non-uniqueness of weak solutions, and the right framework here is to work this in viscosity solutions. Although in this talk, I'm just going to focus actually in the smooth case. The reward is that we obtain a global optimal feedback map. So now the feedback is not, the control signal is not expressed anymore as a function of time, but is expressed as a function of the state. And this is essential if you want to do real-time control. Because if we're doing real-time control, we're not going to have time to compute a Pontryagin principle, for instance, in real time. We only are going to have time, say 1 millisecond, to identify what is the current state of the system and then provide an optimal action. So we need a feedback that is stored somewhere and that allows a call where you provide the current state of the system and returns what is the optimal action. So there's real-time control. But somehow Hamilton-Jacobi PDEs are ubiquitous in all the things other than feedback control. We have a Conal equation for propagation, for rate propagation, Isaac's equation as a generalization of Hamilton-Jacobi equations in differential games. And as by the end of the talk, I'm also going to show that Hamilton-Jacobi equations, they appear in mean field control and mean field games as well. The main bottleneck here, in my opinion, is what we call the reverse of dimensionality. Namely, that this PDE here, you see this boldface X, if I can go back one slide, it comes from the dynamical system here from the initial conditions, so it lives in RD. So this PDE here is a PDE that is cast in a domain where the domain is the state space of the dynamical system that we want to control. So, and this is going to be difficult. I mean, the problem here is that most of our computational methods are written for PDEs in physical space. So we normally work, for instance, if you think about Navier-Stokes or Euler equations, these are at most 3+1 dimensions. But here the dimension of the PDE, of the domain, is arbitrarily high because it depends on the dimension of the state space. So if I go back to my drone example with 12,000 state space, I need to solve a nonlinear partial differential equation in a 12,000 dimensional domain. And this is difficult. In particular, if we want to apply this for controlling partial differential equations, this abstract dynamics is an infinite dimensional system. So we're now writing a PDE in an infinite dimensional space. Of course, this was noted at the birth of viscosity solutions, Hamilton-Jacobi equations by Crandall and Lyons in '85. But the problem here is, besides the theoretical problem, there is also a computational problem on how can we guess optimal feedback controllers for nonlinear partial differential equations. So some of the examples that I'm going to show is about how to control a Berger's equation, or how to control the Allen-Cahn equation with a nonlinear reaction term, or how to control the Fokker-Planck equation, understood as infinite dimensional dynamics So optimal feedback design for infinite dimensional dynamics. So from a computational viewpoint, this is probably the most challenging computational problem in optimal feedback control. I'm sure there are other problems, but being able to solve this equation in arbitrarily high dimensions enables the solution of optimal feedback controls for any dynamics that you might have. So, of course, many people have been working on this for many years in the last, would say, 50 years on how to solve numerically Hamilton-Jacobi equations and try to increase on the dimensions. The curse of dimensionality here is clear that once you discretize your domain, the state space in a grid, for instance, if you do finite differences or the simplest numerical scheme, you will obtain a tensorial grid that has n to the degrees of freedom. So the curse of dimensionality here is really that the computational complexity of solving this problem scales exponentially with respect to the dimension of the problem. And that's the worst of the numerical worlds, would say. And as I was saying, that most of our numerical methods for PDEs are meant for PDEs in physical space. So at most 3+1 dimensions. Except for instance, if you think about Boltzmann equation or a couple of other equations around that are naturally written in a higher dimensional spaces, most of our solvers are for 3+1 dimensions. If you think about finite elements or finite volumes, and you already know that even if we do think, for instance, these simple academic examples that we do about the car, like stabilizing with an inverted pendulum and so on, you can easily already have, for a very, very academic problem, you can already have dynamics that go beyond, I don't know, 4 or 5 states. So this is challenging. And even if you pull all your numerical tricks like high order methods, domain decomposition, adaptivity, that will not unlock the fact that you will not be able to solve 10-dimensional equations. But for moderately high dimensions, for instance, 8 dimensions, so 8-dimensional control problems, one can use sparse grids. In some cases, one can also use max plus algebra. And there are other methods for high-dimensional equations, for instance, the use of representation formulas like Laxkopf formulas or representation formulas for particular cases of Hamilton-Jacobi equations. And what I'm going to show today is the use of tensor decomposition methods for high-dimensional Hamilton-Jacobi equations. This is something that somehow has proven to be very, very effective to scale to very high-dimensional Hamilton-Jacobi equation. And of course, in 2021, many people are working on machine learning and reinforcement learning. And also there is the idea that we can use machine learning or deep learning techniques to solve arbitrarily high-dimensional Hamilton-Jacobi equations. This is a long story. This starts, if you want, from the work by Bersekas in the 90s. At that time, it was not named deep reinforcement learning, but people would call it neurodynamic programming. But of course, there has been some technological upgrades in the last 30 years, and now people are interested again in the use of deep learning techniques here. There are solvers like for stochastic control problems that have effectively solved like 100-dimensional Hamilton-Jacobi equations. There is what's celebrated deep Galerkin method from 2018. These are very recent works of people trying to solve high-dimensional partial differential equation using deep learning techniques. But the first part of my talk is not about deep learning, it's about the classical methods and how far can we push existing numerical machinery to solve high-dimensional Hamilton-Jacobi equations. So it's mostly based on this work with Sergei Dolgov and Kalkunis. Sergei is a colleague who is an expert on tensor decompositions, but they have been using these sort of techniques for other type of problems. A couple of years ago, I managed to get him interested on Hamilton-Jacobi equations, and we have been working ever since on this. So how can we build a solver for Hamilton-Jacobi equation? So the first thing here, one simplification, is that we get rid of the control here of the minimization. If we assume that the control is solved like without constraints, so you can take the full space of where your control variable lives, one can compute explicitly this minimizer. So this minimizer, like when you compute like the LQR, the linear-quadratic regulator, one in a small generalization here, one can express the feedback here as a function of the gradient of the value function and plug it back on the equation and obtain this nicer V1 of more explicit formulation of the Hamilton-Jacobi equation without the minimization, because it's already done and it's plugged back into the equation. Of course, it's still a nonlinear equation. So you can see here there is a nonlinearity with respect to the gradient of the value functions. You have a first order term here, transport, VL, and then you have this nonlinearity. So from this viewpoint, one very pragmatic thing to do to address the nonlinearity is to, okay, let's do an iterative method, let's do a Newton method to solve V. I'm not thinking about the dimension, I'm just first thinking on how to address the nonlinearity in a computational way. So here, there is what is called like a Newton method or a policy iteration for the Hamilton-Jacobi literature. That's the name that people use, which is to build a Newton method for this equation. So building a Newton method here from a control perspective is interpreted in the following way. Let's iterate by fixing an optimal feedback map in the whole state so that this equation here, we don't have to deal with the minimization at a given iteration. So if you get rid of the minimization and you freeze the control, if you freeze the control here at a certain, you make a guess of what could be the feedback map and you freeze it, then you just need to solve a linear equation for the gradient of V, which is what is left to you if you get rid of the minimization and then you freeze the control here and here. If you solve this linear equation, through this formula here, you can create an update of the control variable and apply it back and solve a linear equation and update the control and go on. This is exactly how one would construct a Newton method for this equation here. So this is the first idea. So address the nonlinearity in the Hamilton-Jacobi equation with a Newton method. Why could this be interesting for controlled people? What I'm explaining is because the successive approximation algorithm, like any Newton method, has to be initialized correctly. And the convergence of this algorithm for solving a Hamilton-Jacobi equation requires that you have an initial admissible control. So that's the trick here. The catch is that I can do a Newton method that is guaranteed to converge if I just keep doing this iteration for the Hamilton-Jacobi equation. But if I want this to work, I need first an admissible controller. Admissible in the sense that it's a control that asymptotically stabilizes the dynamic. It's not optimal, but it stabilizes. So actually one thing that I've been reading in order to implement this to the examples that I'm going to show you is what is available in the literature about the existence and the construction of asymptotically stabilizing controllers. So here, if we want to get this loop started, you need a suboptimal stabilizing, asymptotically stabilizing controller. But then, of course, what I can provide you at the end of the day is an optimized and stabilizing feedback control. But still, one need to at least know the existence and the construction of this initial guess of this control that is suboptimal but stabilizes the dynamics. Of course, if the dynamics are already stable and you are just worried about determining an optimal feedback that is going to accelerate an optimal feedback, they are going to accelerate conversions, you can just take the initial guess u equals 0. But in the other cases, you will need to get an initially stabilizing, asymptotically stabilizing feedback. And that's just to get rid of the nonlinearity. Of course, the second trick here is that now I managed to get rid of the nonlinearity. I now have an iterative method that is going to require in every iteration the solution of a linear equation. And here now I have to address the dimensionality. So here now I have at every iteration of this Newton step, I will need to solve this partial differential equation, which is linear. The control here comes from the previous time step, so I know it. I know here everything except the gradient of V. This is not a difficult equation, except for the fact that this is again in this very high dimensional space. So as I was saying, one could not resort to finite elements or finite differences to solve this in a high dimensional space. So one has to think on other type of discretization techniques. So for instance, one thing that we have done in the past is to use a polynomial approximation here, because we know, and this is something that repeats over and over in this talk or in this way to understand Hamilton-Jacobi equations, we know, one thing that we know from control from the first control courses is that if the dynamics are linear, and in the linear quadratic case, we know that the value function is a quadratic function, is a quadratic form. So a natural way to express the value function would be, instead of taking this sort of finite element or finite different answer, to take a polynomial answer, like a globally defined polynomials to approximate the value function, and to do some sort of power series approximation of the value function. That somehow has allowed us to solve, like, to scale up to 15 dimensions, which still at some point was somehow the state of the art. Now, what we do is a bit different, is we use tensor decompositions. What we do is to take a discretization in every dimension of X of the state space, we say Legendre polynomials, and somehow express your value function as a tensor here in many dimensions, times some basis functions that are polynomials, in globally defined polynomials in high dimensions. So the cardinality here is a bit constrained. What is the idea here? Is that we are going to express the value function in a compressed format. So one thing that we need to understand is, in a high dimensional setting, if we discretize, the value function is represented as a grid in many dimensions. So it's a tensor. It's like this grid that I have here in 3 dimensions. You can picture it in your favorite way. How would this look in more dimensions? But it's a tensor. It's just an n-way, d-way tensor with a full tensor. And what we know, for instance, from numerical linear algebra, is that if you work with matrices, we have the singular value decomposition. So for a 2-dimensional problem, the value function over a grid is going to look like this. So you're going to have values in each point of your grid. And one could think about this tensor, about this matrix representing the value function in 2 dimensions. Through the singular value decomposition, one could express this as a sum of one-way tensors of vectors. So in the singular value decomposition, you have up to n terms here, a sum of n of these low rank factors. So it's a way to compress information. Of course, the name of the game is that ideally, this object here can be accurately represented with a sum of these folks here, but they are not that many. So hopefully, when we work with compression, we try to work with a sum that doesn't have many terms here. And that's what we know about the singular value decomposition for 2-way tensors, for matrices. But we can extend this to higher dimensional objects. So for higher dimensional objects, the same logic applies, can be constructed. So one can compress, for instance, a 3-dimensional tensor into a sum of a product of low rank factors here. What is the gain here? That in terms of storage, here you would need to have stored n to the d degrees of freedom. And this is the thing that I cannot afford in very high dimensional spaces. But if I do this sort of low rank expansion, I would need d times n degrees of freedom. So I'm moving from an exponential scaling from respect to the dimension to a linear scaling from respect to the dimension. And that hopefully allows to solve the solution of very high dimensional problems. So the question here is, how can we compress a high dimensional tensor with a d-way tensor into sums of low rank factors? And there is something that people in numerical linear algebra somehow has been working for ages. And one of these breakthroughs in this area is what is called the Tensor Train format, is from 10 years ago, which is that a d-way tensor can be expressed like in this row here at the bottom as a concatenation here of 3-way tensors, and plus one 2-way tensor at the beginning and 2-way tensor at the end. That's what is called train, right? It's just a concatenation of products of 3-way tensors. So it's really expressed as this sum that I have here on top. This thing here, each one of them are 3-way tensors. So you have 1, 2, 3 parameters. But of course, you sum over 2. So this, when you freeze these 2 indexes, what is left to you is a one-way tensor. Of course, the name of the game here again is, we can do this. The question is that if we really want to scale linearly or do want to a good performance with the dimension, we need that these ranks, these arcs there, do not blow up, because then we don't gain much from this sort of compression. But if we can express, in some cases, if we can express or we can characterize class of control problems where the value function can be expressed as this concatenation where the ranks here are not very high, then we're in good shape to compress the value function here. In particular, for instance, you could have like it's like separation of variables in a certain sense. It's like separation of variables. So we're going to express things as products of one-dimensional things. The problem, of course, the catch is that we're not anymore. You need to somehow rework the numerical linear algebra, because what does it mean to solve a linear system? Let me, go back here. My original problem after discretization here is the solution of a linear system. And this is something that I know how to do if I just work with the full tensor. On the other hand, when you work with this sort of compression, one would need to rethink what does it mean to solve the linear system if the data is expressed in this way. So there is a bit of tensor calculus here that one needs to redo but there are algorithms. So for instance, one well-known algorithm in this area is the alternating least squares, which is sort of a projection-based approach to solve these high-dimensional problems where the data that you are looking for is expressed in this format. I'm not going to bother you with these details, but I just want to say that we do have results here. As I say, the main question is, can we characterize the class of control problems where the value function we know can be compressed in that way, such that somehow the computational complexity of this problem scales linearly with respect to the dimension? And we have some partial positive answers. So they are not very surprising because they are still limited to the linear quadratic case. But for instance, in the linear quadratic case, under certain stabilizability conditions and properties of the closed loop of the Riccati equation, and more importantly, if we're able to bound the rank of the off-diagonal elements of this system, we can obtain bounds, upper bounds for the ranks, for the number of terms that these expansions are going to have. So one detail here, what I think is interesting, is that what appears here is that this M, for instance, this capital M parameter here is governed by the rank of the off-diagonal elements that appear here in this. And now, if you think about discretization of PDEs, imagine that this A and B that I write my original infinite dimensional dynamics, I discretize it with finite elements or finite differences or whatever to express this as a finite dimensional dynamical system. For instance, when you discretize the Laplacian, you get here a matrix A that the off-diagonal elements, they have very low rank. So this M here is well behaved. But if you think, for instance, now about the no local problems, if you discretize, for instance, fractional diffusion or no local transport operators, this matrix A is going to reflect that no locality. So these ranks here are not going to very well behave. So this M here is going to grow, and then the ranks that you are going to achieve for this compression of the value function are not going to be very good. I'm not saying they are going to be bad. I mean, we're checking this, but I mean computationally, but is better in the local case. And that makes a lot of sense, because if we think about local PDEs, maybe it makes sense to linear local PDEs that the value function has this sort of nice separability along the dimensions. But when you are dealing with the non-local case, it's somehow unsurprising that these estimates are going to deteriorate. But this is some things that we're interested to achieve this, understand this characterization of control problems where this value function admit this sort of compression. So let me show you some examples before we go into the machine learning part. So here's an example, the stabilization of the Allen-Cahn PDE. So one-dimensional example. Imagine that we have this PDE where you have second derivative. Here's an evolution equation, derivatives, and then the nonlinearity here, x minus x cubic. and a control that is scalar in time, but is confined to a part of the domain through an indicator function. So it's 0 in most of the domain, is 1 in a subset, and then you are trying to optimize this U as a feedback, the optimal feedback. With Neumann boundary conditions. With Neumann boundary conditions, the nonlinearity gives rise to a stable potential. So you have 3 equilibriums of these dynamics, -1, 0, and 1. But the initial conditions will naturally, the uncontrolled dynamics, they naturally converge to +1 or -1, depending on where you are. Of course, what we want to do with control is to remove this structure, and through the control stabilize these dynamics towards the unstable equilibrium x = 0. So the first thing that we need to do, and this is the logic a little bit, is to bring this infinite dimensional dynamics to a finite dimensional dynamical system, because everything that I show for the Hamilton-Jacobi equation is for finite dimensional systems. So we do, for instance, collocation points or finite element discretization. We obtain an accurate approximation of these dynamics, say, for instance, but now they are represented by a 40-dimensional dynamical system. And we apply these sort of techniques. It takes, say, 1 hour to compute this with 40 dimensions, which is quite good. So it's something that one can compute in your laptop. And we observe is the following. So for instance, here I'm showing you the running cost. So the running cost and the total cost associated to this design. Of course, the uncontrolled dynamics, they go stack to x = 1. So the cost is just infinite. One thing that people normally do in optimal control, suboptimal control of nonlinear dynamics, is to linearize and plug the linearized controller into the nonlinear dynamics and hope for the best, at least locally. In this case, for instance, the LQR will give you a cost. If you just work with the optimal control of this part around 0, and you plug it to the nonlinear case, well, this nonlinearity is actually helping you, but it's still suboptimal, right? So the LQR will have a finite cost, the linear-quadratic regulator, but of course, by addressing the problem in its whole complexity, so truly addressing the nonlinearity, not just by linearizing and neglecting it, you obtain Hamilton-Jacobi controllers, optimal feedback controllers that are better in performance. So they are still suboptimal because of the discretization, but you are truly trying to do optimal feedback synthesis. What is interesting here is the difference between the red line and the blue line. So because here, how do you approximate this? Some sort of a model approximation, a finite dimensional projection of the system, you can control it. So you can either control, if you think about like a spectral approximation, you can control a finite number of modes of your interest. And it makes a difference how many modes you control. So for instance, if these infinite dimensional dynamics are approximated by a 14-dimensional, by the first 14 modes, and then you do the controller and you plug it into the infinite dimensional system back, you're going to obtain a certain performance, which is not as good as if you genuinely try to go for more modes to a better description of the dynamics. You synthesize your feedback and you plug it, you obtain a cost that is still smaller. And you can see that there is a difference between the control signals. So the control signal here from the LQR is different from the control signal from the Hamilton-Jacobi for the 14 modes approximation, and is different from the Hamilton-Jacobi feedback from the 40 modes. But really, keep in mind, these 40 modes mean that I'm solving a 40-dimensional partial differential equation. And what is interesting from a computational viewpoint here is that here the number of the rank here remains well behaved with respect to the dimensions. Sorry, it's like a little break, a technical difficulty. Just my pointer had just vanished for 1 second, but we're back. So here, the other thing here that is worth to have a look is that actually the ranks, they don't blow up as you increase the dimension of the problem. And that's what I was expecting, that somehow this compression does not deteriorate when the dimension of the problem grows. Other thing that maybe is interesting for some of you is the fact that I was making the assumption that the control remains unconstrained. Of course, as you impose a box constraint, the value function loses regularity. This compression does not work very well. But at least we know that it is possible to enforce box constraints on the control through the action of penalties. So for instance, if instead of having a U-squared penalty, we replace it with say a hyperbolic tangent type of function, it is possible to design controllers that respect some lower bounds of your interest. So as you can see here, I artificially impose through penalties box constraints on the control signal, but of course the price that you pay is that you impose a box constraint, the value functions loses regularity or loses like the nice shape, and then the ranks, they start increasing. So you have to look in the other way. So as the constraints become more demanding, the box constraint becomes more demanding, the ranks of the representation of the value functions start increasing, and this is not good. It still works, but this is much better if you do one constraint problems. But we can even, just to say, we can even scale to now do feedback control of two-dimensional PDEs. So two-dimensional PDEs, if we think a discretization of these dynamics now in 2 dimensions, they will naturally give rise to, I don't know, hundreds of state variables. Here, with this sort of solver, what we could push for the most was the over 100 degrees of freedom. So 120, if I recall correctly, 120 dimensional Hamilton-Jacobi equation just to compute the optimal feedback synthesis of these just 2 versions of the Allen-Cahn equation. We also apply this, for instance, for the control of the Fokker-Planck equation. The Fokker-Planck equation is stable. The thing is that what you want to do here is to accelerate convergence to the stationary state, to invariant measure of the Fokker-Planck equation. So here you can initialize the Hamilton-Jacobi solver with a 0 controller. And just to show you that we can also apply these to control problems that after discretization will still have some sort of bilinear control structure. So it's a bit more sophisticated than just for linear control problems that have a nonlinearity fully decoupled from the control. So bilinear control problems are also possible to address in this framework. But somehow this is, up to what I know, this is how far can you push this sort of grid-based discretizations with this sort of tensor techniques. As a bit of the state of the art of grid-based discretizations, but still, honestly, this scales as good as machine learning techniques. With this sort of tensor decomposition techniques, we're at the same level of high-dimensional problems that people in model-based reinforcement learning are trying to solve for this type of dynamics. But of course, we also have an interest on how far can we go. Is there anything to say from interesting from machine learning point of view of a learning point? So the second part of the talk is a bit without discretization of the Hamilton-Jacobi equation, but thinking about some sort of type of machine learning algorithms for the solution of the value function. So one idea that we had here is that, again, we stick with the global approximation. So we're going to think that the value function is represented not through a neural network, but is represented through a linear expansion of coefficients times some multidimensional polynomial basis. As again, this is somehow inspired from the fact that we know that there are some good results regarding power series expansions of the Hamilton-Jacobi equation, and because we know that we can, that in the linear quadratic case, the value function is a quadratic form, so it's naturally expressed in this way. One interesting result here is that in certain cases for the Hamilton-Jacobi equation, there are what we know as representation formulas. So for instance, we have one remarkable old example from this is the Laxkov formula. For this particular case of a Hamilton-Jacobi equation, we know that the value function at xt is expressed as a convex optimization problem, point-wise, that depends on like Legendre transform of the initial condition and some terms here. So this is like a PDE aspect, like a representation formula for the Hamilton-Jacobi equation. This means that if you don't want to know the whole Hamilton-Jacobi equation, the whole space, but you just want to know the value in a given space-time point, a given point in space-time cylinder, what you need to do is to solve a finite dimensional convex optimization problem, which is a task that numerically we can do very, very effectively. So that somehow there is like a philosophical discussion there of what does it mean to solve a PDE? Do I want to recover a numerical approximation that I'm going to store in a computer and then I'm just going to interpolate values from there? Or is it okay for me if to know the feedback control, I need just to know the value at the given point where I'm currently are? And if I can do this convex optimization task sufficiently fast, then I'm done with it. So this is but there are representation formulas. And in the more control-oriented case, one could also think about Pontryagin maximum principle as a representation formula for the Hamilton-Jacobi equation. And again, these are things that are effectively solved and efficiently solved through primal dual algorithms or two-point boundary value problems. So one idea that we had at some point is, okay, let's use these representation formulas to generate what is called like synthetic data, to generate training data, to do regression and to build a model for the value function. So we can sample 1,000 points for which we realize these representation formulas or this Pontryagin maximum principle. So we obtain a approximation of V, we label this data, and then we do regression to learn the coefficients of this value function. So it's really like, and then when we learn the value function, we learn the gradient, the optimal feedback just as the gradient of the object that we learn. Of course, in finite horizon control, what is interesting, because this Laxkov formula here that you see for this PDE is really not relevant for control problems. I mean, it's not representative of the sort of state-dependent dynamics and state-dependent cost that we might have. But if you were to have something like a finite horizon control problem, you will have the Hamilton-Jacobi equation, a variant of what I wrote before, just a time-dependent one. But if we go through a Pontryagin maximum principle, for a given initial condition, we can identify the optimal control through the solution of this two-point boundary value problem. So the state equation going forward, the adjoint equation going backward, and the relation for the optimal control. And that will give you the solution, and it's not a feedback, it's just going to give you the optimal control for a given initial condition. But still, if you sample many initial conditions, then you can somehow reconstruct the feedback in the whole space. But of course, here there is a contentious issue, because this is a bit of a heresy for people in optimal control, because what we know is that Hamilton-Jacobi equations are going to give you sufficient, like global optimal controllers, but Pontryagin is just going to give you sufficient sufficient optimality conditions. So one has to be here careful to restrict yourself to the class of optimal control problems where Pontryagin is also necessary and sufficient. So, but there is some literature here, rather technical, that goes from Barmitz in 85 and Subbotina, and actually there is a nice review of these works in this paper by Yegorov and Dower from 2017 on identifying context frameworks where Pontryagin can be correctly identified as the characteristic curves of the Hamilton-Jacobi equation. So in the smooth convex case, one can claim that the Pontryagin maximum principle corresponds to the characteristic curves of the Hamilton-Jacobi equation. So there is nothing wrong in solving Pontryagin, integrating these trajectories, and understanding that by doing so, you are fetching information from the value function. So you solve Pontryagin, and then one can recover the value function. And more importantly, by the gradient of the value function is given by the adjoint of this solution. So this is what. So now I can really solve in a cloud of point Pontryagin, and then use this to recover a value function based on the information of both the value and the gradient. So this is an enriched regression, because I'm not only recovering V, but now I'm going to learn a model for V based on information on V and gradient of V. Because the adjoint, once I solve the Pontryagin, I just have it for free. So that's and that's a good thing. One would need, of course, to set a solver for solving these many open loop control problems. And then one can do, if we have a linear ansatz, a polynomial model here, one could do like a lasso regression. So it's a very, very effective optimization for the regression of the coefficients here. So there is no need to go to like stochastic gradient descent and all these variants that are not very, very efficient sometimes. But we work, as I said, with a polynomial model. And now the problem is that I'm going to learn this polynomial model based on points information of the model plus information of its derivatives that I obtain through the adjoint. One question here is, how do I express my value function? So here, what is the polynomial basis that I want to take here? There are different options. One could take tensor product monomials, or one can take total degree. In this case, we use what is called a hyperbolic cross approximation. So there are ways to select a polynomial basis for this problem. Of course, the thing is that one wants to choose a basis that the cardinality does not blow up with the dimension. Of course, if we take like a monomial, full monomial basis, like you take all the possible monomials up to a certain degree, this explodes exponentially with respect to the dimension. If one takes a total degree basis, so you think, I'm in the dimensions, I'm going to take all the monomials that go up to degree n, this is going to depend combinatorially. It's not very good. But if one takes the hyperbolic cross approximation, so just a more restrictive way to trim these total degree monomials, one actually can scale fairly well, as I'm going to show you in the examples with respect to the dimensions. And then there is just the matrix assemble. We sample 1,000 points, we solve point triaging, we assemble the matrices that contain information of the value function and the gradient. We assemble these sort of van der Monde matrices, and then we cast least square problems for learning the coefficients of the value function. And on top of it, we put some sparsity by doing the regression with respect to the gradient and value function information. But on top of it, we do a regression with respect to with the sparse regression. So we also penalize sparsity in theta. That means that the polynomial expansion that I'm going to obtain for the value function is going to have a lot of zero elements. It's going to be very compressed with as few monomials as necessary. So the feedback computation is going to be quite effective. So this is what I mean here. Well, this is just the typical lasso iteration. That's fine. So believe me, there is like very good convex optimization algorithms to solve this sort of regression problems that I have here. And here, what I have is I have my expansion. And as I say, since I'm doing an L1 minimization, there are many of these thetas that are going to be zero. So the cardinality of the say expansion of the value function is going to be very reduced. So this is high dimensional, but on the other hand, when we do the expression of the value function, we're going to obtain just a few non-zero monomials. Just some examples to illustrate. So for example, just a low dimensional example first to express things. A let's say non-linear van der Pol oscillator, have non-linear dynamics here, linear control. We want to stabilize to the origin. And we have, of course, the sampling data is just for reference. I was using much less points. What you can see here in the table, let me explain. The first row shows you what you will get if you do a regression for the value function only using point-wise values of the value function. So somehow I solved point triaging, I obtained the value function, but I forgot that the adjoint is the gradient of the value function, which is a mistake because that you are getting information for free. The second row here shows you how do you fix this. So if you do with the same data points, but now you also recover the gradient, the adjoint information that is given you for free, you have much more information to do the regression. So you see that the errors, the regression errors, they decrease by 2 orders of magnitude, because with the same computational cost, just because I'm using all the information that the point triaging principle is giving to me. But I'm doing this with the L2 regression without sparsity penalization. So from the 52 coefficients that I give to my expansion, the 52 were used. So this is like a big expansion for the value function. And in the last row, I have gradient information, but I introduce also the L1 minimization. So I also penalize the sparsity on the expansion of the value function. I obtain a little error here. And on top of it, I obtain the same error more or less as in the L2 minimization, but the gain here is that now I have just 19 out of 52 non-zero components. So the sparsity really takes out all the monomials that are not giving much information. So now the value function is as accurate as the other one, uses very few sampling points. So you just need 40 sampling points, 40 solves of this point triaging principle just to learn the optimal value function, the feedback map, and express it in a very compressed way. The same we extend it to agent-based models. So in agent-based models, for instance, are here like a consensus problem. So have no linear dynamical system for second-order agents, where the name of the game here is I want to steer all these agents to travel in the same velocity. That gives rise to a problem in 80 dimensions, but they still are able to learn this 80-dimensional value function just by regression and to have a very sparse representation of this. Here, the only thing that probably you need to get from this plot is that the difference between this 70 and this 4,000 here is really the 70 here. It means how many samples do I need to achieve the same error, depending on whether I use the gradient information that comes from the adjoint in the regression or not. So actually this idea of using the gradient information, using the adjoint from the point training really, really makes your life easier, and you still are being sparse. So I'm not going to talk about this, I'm afraid, but how can we extend this to infinite horizon problems? Because we don't have something nice as the Pontryagin principle for infinite horizon problems. I mean, or it's difficult to set numerically. We use what we call the state-dependent Riccati equation. So this is like we solve the Riccati equation for many linearizations of the problem, and then we train, in this case, not regression, but we train an artificial neural network with the same idea, and we use the gradient information as well by just linearizing and solving the Riccati equation in a cloud of points. Again, we have a lot of good solvers for the state-dependent Riccati equation. The same problem in one dimension of the uncontrolled and uncontrolled velocities in the Cucker-Smale problem. And again, we can do up to 80 dimensions. Now is the optimal feedback coming from the infinite horizon stabilization, a cloud of points, linearization, solving the Riccati equation, fetching this data and the gradient data to learn the value function for the whole, the nonlinear value function for the whole problem. It's not exactly the value function in this case, it's just one can show is a Lyapunov function of this control problem. So this is not the optimal feedback stabilization in any case. Just as a final remark, we're also interested, I was showing multi-scale dynamics in the beginning. So what happens if I have more than 20 or 100 agents? So at some point, this machinery of either machine learning or Tensor decomposition will not sustain such a high dimensional problems, in particular the sort of agent-based consensus problems like I was showing here. In this case, we have what we call nowadays the blessing of dimensionality, not the curse of dimensionality, but the idea is that through statistical mechanics sort of arguments, when you have infinitely many agents, we do mean field modeling. So instead of working with the microscopic position, say, of each one of these agents, we work with the density function of the agents. But of course, that gives you rise to a non-local transport equation, but then we're back to do PDE control, just to control the density of the agents. So we're back again to, say, if you want open loop, not to optimal feedback, but to open loop for a given initial density of agents. But when we derive optimality conditions, the adjoint of this transport equation will look pretty much like a non-local Hamilton-Jacobi equation. So just the punchline is somehow Hamilton-Jacobi equations in these sort of things are everywhere. It's difficult to avoid. We use this, for instance, to do control of opinion dynamics. So if you need, you have agents, microscopic agents that when they evolve in time, they tend to concentrate around certain, self-organize around clusters. Through the mean field PDE of the density, we record the same sort of structure here. This is evolution in time of the distribution of agents. So there is a mean field clustering as well that is well recovered. But of course, with control, we remove that structure and we stabilize towards a given density. But this is really a forward-backward system of a non-local transport equation coupled with a non-local Hamilton-Jacobi equation. So that's the way that we do control synthesis when you have many agent-based models. And this is the same, it looks pretty much like mean field gains where you have Fokker-Planck equations coupled with Hamilton-Jacobi equations. Just to close, yeah, this is optimal feedback control in general for high-dimensional nonlinear dynamics. Of course, what we're looking at the moment is the idea of trying to scale and combine this with multi-scale dynamics. So we are now at the moment where we really want to control kinetic equations like Boltzmann equations. So we really are working with the densities and agents, trying to concentrate the density and doing optimal feedback control for these problems. But again, it would go to do feedback control somehow to the Fokker-Planck equation, as I was showing in the tensor decomposition part. There are other interesting problems related to controlling swarm robotics. So one can really use these agent-based models, as I was showing in the beginning, for modeling the interaction between drones and trying to have them achieve a formation space. But again, this has to be done with feedback. At the moment, people are using feedback. The thing is that the feedback that they propose are non-optimal. So they are suboptimal. They are just ad hoc design. And again, this sort of technology would unlock the solution of optimal feedback problems for very high dimensional problems of this type. As you know, there is a duality between control and estimation. So all the things that we have looked is in control design, like in the same way that you have LQR and Kalman filter. Of course, an open problem here is how can we use this methodology to solve also optimal estimation problems that are as equally as interesting as the optimal control problems. And we're also in the moment looking at the use of tensor decomposition techniques for reinforcement learning. These are the references. If you want to have a look, we do have the Tensor Train decomposition solver publicly available. So Sergey, the collaborator, is an expert in tensor decompositions, and he wrote this very, very nice suite of codes to solve the very high dimensional nonlinear control problem with this sort of tensor decomposition. So please have a look. Just a commercial advertisement. In starting in July, I'm moving to Imperial College in London, and I'm starting like a small group in these topics. So I'm advertising some positions like PhD and postdoctoral positions. So if you are interested on these, or you know someone who is interested, please do contact me. I'll be very happy to discuss about this. So thanks for your time. I'm sorry I went a bit out over time, I think. Yes, I'm very sorry, but please, thanks for your time, and please, any question. Yeah.
Okay. Thank you very much, Dante, for this very nice talk. We have time for some questions. I don't know if some of the public, any question or comments.
Can I make a question?
Please, Alessandro. Yeah.
Dante, I missed something when you presented the first algorithm. I think it's one of the first slides when you present the linearized version of the HJB equation.
Yes, please.
So the part lambda VK, I mean, you don't put the linear part, I mean, the lambda times V. Why? Maybe I'm missing something. So if you see step 3 in your algorithm, it just depends on the gradient.
Yes, yes, thanks for your question. The discount factor, somehow, if you put a discount factor, you're not necessarily going to get that optimal stabilization, right? So at the end of the day, you would like to solve these things with lambda equals 0, because then you will have optimal feedback stabilization. What we do numerically, of course, the more general equation is written with lambda. What we do in many cases is to do a continuation with lambda. So normally what we do is we start with a certain lambda because this problem is easy. So the lambda here comes here. So for those, this relaxes the requirement of asymptotic stabilization. We normally start with a lambda different from 0. We solve this problem. We go through the full Newton iteration, and when we obtain this solution, we start doing a continuation with respect to the lambda. So we shrink little by little the lambda up to a point where lambda goes to 0, and then at the end we're able to. But if you want to solve this without lambda, yeah, what we recommend is to do this sort of continuation and starting with a big lambda. Yeah.
But why you're interested directly on lambda equals 0? That's because I mean usually lambda should be greater than 0 to get convergence on the integral.
Because the control problem here, you want to design an optimal feedback that drives you, for instance, to y equals 0. If you have a positive lambda, you don't necessarily will have that. Optimal stabilization will come with lambda equals 0. So asymptotic stabilization to the origin. So that's. Yeah, I know that people are normally interested in lambda greater than 0 because it makes their life easier. But the things that, for instance, minimum time problems or optimal infinite horizon optimal feedback stabilization, the true thing, like the LQR doesn't have a lambda. No, you can put a lambda, but the original formulation, it doesn't have one. Yeah.
Yes. And then I mean basically you're just interested in the gradient of the value function.
Yes. Yeah. the problem here is not at this level. The problem, you know, is not the BE. Is solving the high dimensional thing. Yeah. Yes.
Yep. Thank you.
Yes. Yep. Welcome.
Okay. Thank you very much. Another question or comments? You can write in the chat or take your micro. Dante, just for curiosity, the relation of the Pontryagin equation and the characteristics of the Hamilton-Jacobi, the theorem you say was the smooth case, no? For
yes,
there is something about the something not non-smooth. Can have a
no, I don't know. I think there is. I think there are people who also work on yeah, some characterizations of cases where there are sufficient conditions. I'm really not. I haven't read, but there are. But and if somebody knows, I'm very happy to hear. But I'm just working on the simplest case. No. But this is an extensive. There is a discussion, you know, where you can. This is in the book by Vardian, Capuzzo, Olched, and Hamilton-Jacobi equations. There is a chapter where they discuss at a very technical way the link between conditions for Pontryagin type conditions and the value function, because you have all this. It's very easy to break this structure down just by construct some very simple example that has a state constraint, a control constraint, or just some dynamics that are non-smooth, and all this breaks down. But there is a characterization, but it's very technical, and it's not off the top of my head at this moment. But
yeah, I see.
Yeah.
Very interesting. Thank you, Dante.
Okay.
Okay, I don't know if there is another questions or comments.
Okay.
If not, thank you very much, Dante.
Thank you. Thank you, everyone. Yeah.
We thank the
Thank you.
Dante, and thank all the public. We hope next week with 2 junior speakers as usual. So see you. Okay. Thank you again, Dante.
Okay.
Very nice
Bye.
talk.
Thanks. Thank you.
Bye bye. Thank you.
Bye.
Thank you very much.
Bye bye. Thank you again.